Hello, my name is Juan Gómez-Luna, and I'm a senior researcher in the Safari Research Group at IEDM Zurich. I'm going to present our work, Understanding a Modern Processing in Memory Architecture, Benchmarking and Experimental Characterization. Let's start with a brief executive summary. In current computing systems, data movement between the memory and storage units and the compute units is a major contributor to the execution time and the energy consumption. Processing in memory is a promising paradigm that can tackle this data movement bottleneck. Processing in memory essentially consists of placing compute capabilities near or inside memory. Although explored for more than 50 years, technology challenges prevented from the successful materialization. UPMEM has designed, fabricated, and commercializes the first publicly available real-world processing in memory architecture, which consists of DDR4 chips embedding small cores called DRAM processing units or DPUs. Our work is an introduction to the UPMEM PIM architecture and programming model, a characterization of the DPU architecture, and a benchmarking and workload suitability study. Our main contributions are a comprehensive characterization and analysis of the first commercially available PIM architecture and the first benchmark suite for a real-world processing in memory architecture that is called PRIM. PRIM contains 16 workloads that are memory-bound in conventional processor-centric systems. We characterize these workloads with a strong and weak scaling analysis and compare them to their state-of-the-art CPU and GPU counterparts. Main takeaways of our work are the workload characteristics for PIM suitability, programming recommendations, suggestions and hints for hardware and architecture designers of future PIM systems, and PRIM, which can be used as programming samples and for evaluation and comparison of current and future PIM systems. Data movement in current compute systems dominates performance and energy consumption. So, according to recent studies, data movement accounts for 62% of total system energy in consumer applications, 40% in scientific applications, and 35% in mobile applications. If you take a look at a current system on chip, you will find many components like CPU, GPU, cache hierarchy, accelerators, and among all these components and the DRAM, there is a lot of data movement. This data movement entails a huge bottleneck that can be alleviated by making compute systems more data-centric. And processing in memory is a way of doing it. Processing in memory proposes computing where it makes sense, where the data resides. The UPMEM PIM architecture consists of DDR4 DIMMs with PIM chips that contain memory arrays and small processors called DPUs. In our paper, we present this architecture and perform a thorough benchmarking and experimental characterization. Throughout our paper and also throughout this presentation, you will find some color boxes with programming recommendations, key observations, and key takeaways. Let's start with an overview of a UPMEM-based PIM system. The integration of UPMEM DIMMs in a system follows the accelerator model, where the UPMEM DIMMs are seen as an accelerator or a coprocessor. In this model, the data movement needs to happen between the host main memory, the host processor, and the accelerator, and this data movement needs to be explicit. Also explicit needs to be the kernel launch onto the UPMEM processors, being the kernel the function that is going to be executed onto these UPMEM processors or DPUs. This resembles GPU computing. Typical system organization is something like this, with a host CPU connected to some DRAM DIMMs that represent the main memory and some UPMEM DIMMs that represent the PIM-enabled memory. Inside each UPMEM DIMM, there are 8 or 16 chips, which means 1 or 2 ranks of 8 chips each. And if we take a closer look at the PIM chip, we will find some DRAM banks that are called MRAM of size 64 megabytes and 8 DRAM processing units. In total, there are 64 DPUs per rank and also 64 MRAM banks. In our work, we have used a system with 20 UPMEM DIMMs that features up to 2,560 DPUs and 160 gigabytes of PIM-enabled memory. We have also used a smaller system with 640 DPUs and 40 gigabytes of PIM-enabled memory. We can give a few hints about UPMN programming and about the interaction between the CPU and the DPUs. Our first programming example is vector addition, one of our benchmarks. In vector addition, we perform the element-wise addition of two input vectors A and B and store the result in a vector C. What we do in the UPMN-based bin system is partitioning the arrays across DPUs, and also inside each of the DPU, we have software threads running that are called Tasklets that process the data that has been assigned to each DPU. The CPU communicates with the DPUs via transfers from main memory to the PIM-enabled memory that we call CPU-DPU transfers, and transfers from the PIM-enabled memory to the main memory that we call DPU-CPU transfers. There are three types of these transfers. There are serial transfers when we are targeting a single DPU and a single MRAM bank. There are parallel transfers when we perform the transfer to multiple DPUs at the same time. And there are broadcast transfers when we transfer a single buffer to multiple DPUs. There is no direct communication channel between DPUs, and this means that the inter-DPU communication takes place via the host CPU using CPU-DPU and DPU-CPU transfers that obviously entail an important overhead. There are some example communication patterns among our benchmarks. For example, merging of partial results to obtain the final result, or redistribution of intermediate results for further computation. How fast are these transfers? We measure these using 2 microbenchmarks and 2 experiments. In the first of our experiments, we use a single DPU and we vary the transfer size from 8 bytes to 32 megabytes. So here we see the results for the bandwidth results for CPU-DPU transfers, for DPU-CPU transfers, and a key observation is that larger CPU-DPU and DPU-CPU transfers between the host main memory and the MRAM banks result in higher sustained bandwidth. We also run experiments on one rank. In this case, we vary the number of DPUs from 1 to 64. These are the bandwidth results for serial transfers. These are the bandwidth results for parallel and broadcast transfers. And one key observation is that the sustained bandwidth of parallel CPU-DPU and DPU-CPU transfers between the host main memory and the MRAM banks increases with the number of DPUs inside a rank. Now, let's take a close look at the DRAM processing unit and characterize it. So if we take a look inside a pin chip, we will find a DDR4 interface for the host to access the DRAM banks. We have a control status interface for the host to send commands to the DPUs. We find 8 of these DRAM banks called MRAM of size 64 megabytes and a DMA engine to access it. We have 2 SRAM-based memories, one for instructions and one for operands called WRAM. And we have the DPU pipeline. This DPU pipeline is an in-order pipeline, and today it can run at a frequency of up to 350 megahertz. It's a fine-grained multi-thread architecture with up to 24 hardware threads and contains 14 pipeline stages. We measure the arithmetic throughput for different data types and operations. What we do is reading an array, moving it to WRAM, and streaming over this array, performing read, modify, write operations. We run our experiments on a single DPU. These are the results for integer 32 and 64-bit values, and these are the results for float and double values. These are the results for addition and subtraction, and these for multiplication and division, and these are the results for the rest of data types. One key observation is that in all cases, the throughput saturates at 11 or more tasklets, and this observation is consistent across data types and operations. Another observation is that there is a large throughput difference between integer and floating point, and also between addition, subtraction, and multiplication division. The reason is that DPUs provide native support for 32 and 64-bit integer addition and subtraction, leading to high throughput, while they don't have native support for multiplication, division, and floating point operations. These operations are emulated by the UPMN runtime library, which leads to much lower throughput. In our paper, we also analyzed the access to WRAM. But now, let's take a look at the access to MRAM. We measured the bandwidth to MRAM for different access patterns. We use different microbenchmarks. First, we measure the latency of a single DMA transfer. Then we also implement the stream benchmark to measure the bandwidth of the stream benchmark and benchmarks for strided and random access patterns. Let's start with the latency of a single DMA transfer. So here, for different transfer sizes, we are going to show the latency and bandwidth of MRAM read and MRAM write transfers. The MRAM bandwidth can be obtained from this expression after measuring the MRAM latency. One thing we notice is that we can model the MRAM latency with a linear expression, something like this, where the MRAM latency is equal to a fixed cost alpha and a variable cost beta times size, being size the size of the transfer. We notice that our model matches perfectly the MRAM latency measurements. And according to our measurements, this beta equals 0.5 cycles per byte. This way, the theoretical maximum MRAM bandwidth is 700 megabytes per second, and our measurements are quite close to that. One key observation is that the MRAM bank access latency increases linearly with the transfer size, and also that the maximum theoretical MRAM bandwidth is 2 bytes per cycle. Now let's take a quick look at the results for the stream benchmark. We have the 4 versions of the stream benchmark, but we have 2 versions of the copy benchmark. One thing we notice is that for some of these, the throughput saturates at less than 11 tasklets, while for others, scale and triad, the throughput saturates at 11. This is because when the access latency to an MRAM bank for a streaming benchmark is larger than the pipeline latency, the performance of the DPU saturates at a number of tasklets smaller than 11. This is a memory-bound workload. However, when the pipeline latency for a streaming benchmark is larger than the MRAM access latency, the performance of the DPU saturates at 11 tasklets. This is a compute-bound workload. In the paper, you can also find results for strided and random access patterns. Now, let's take a look at the arithmetic throughput versus the operational intensity. In this experiment, we want to characterize memory-bound and compute-bound regions for different data types and operations. What we do is moving one chunk of data from MRAM to WRAM, performing a variable number of operations on the data, and write back to MRAM. This is inspired by the roofline model that represents performance versus the arithmetic or operational intensity. In our work, we define operational intensity as the number of arithmetic operations performed per byte accessed from MRAM. The pipeline latency changes with the operational intensity in our experiments, but the MRAM access latency is fixed. We can take a look at these results for addition of 32-bit elements, and what we observe is that there is a memory-bound region where the arithmetic throughput increases with the operational intensity, and there is a compute-bound region where the arithmetic throughput is flat at its maximum and saturates with 11 tasklets. The throughput saturation point is the operational intensity where the transition between the memory-bound and compute-bound region happens, and this throughput saturation point is very low. It's actually very low for all data types and operations. The arithmetic throughput of the DPU saturates at low or very low operational intensity, and thus the DPU is fundamentally a compute-bound processor. So we expect that most real-world workloads will be compute-bound in the UPM-PIM architecture. Let's take a look at the PRIM benchmarks. The idea is to come up with a common set of workloads that can be used for different purposes, like evaluating the UPM-PIM architecture, comparing software improvement and compilers, comparing future PIM architectures and hardware, etc. We use 2 selection criteria. We select workloads from different domains and also workloads that are memory-bound on conventional processors. We have a total of 14 workloads and 16 different benchmarks. If we take a look at the applications domain, we will see dense and linear algebra, databases, graph processing, neural networks, bioinformatics, etc. All these workloads fall in the memory-bound area of the roofline on a Intel Xeon CPU. And these workloads are also diverse. They have different memory access patterns, computation patterns, and communication synchronization patterns, either intra-DPU or inter-DPU. We evaluate with strong and weak scaling experiments and also compare them to CPU and GPU. We use two UPMM-based systems in our evaluation, and we have strong and weak scaling experiments on 1 DPU, 1 rank, and up to 32 ranks. We also compare two UPMM or UPMM-based systems to CPU and GPU. Here you can see the results for a strong scaling of 1 DPU. Here we changed the number of tasklets from 1 to 16, and we show the breakdown of execution time for the DPU kernel time, inter-DPU synchronization time, CPU-DPU transfers, DPU-CPU transfers, and also the speed up over 1 tasklet. Some observations are that the best performing number of tasklets is typically 16 for most of the workloads, and this leads us to this key observation. A number of tasklets greater than 11 is a good choice for most real-world workloads. Another observation is that some of these workloads don't need intra-DPU synchronization primitives, and in others, synchronization is lightweight. But in 3 of them, where they use mutexes, there is a lot of contention due to the access to shared data structures. For example, in one of our versions of histogram, we have tasklets inside a DPU updating a common histogram. And because they need to use mutexes, we see that the best performing number of tasklets is not 16, but 8, due to the contention in the access to the shared histogram. So intensive use of intra-DPU synchronization across tasklets like mutexes, barriers, or handshakes may limit the scalability, and the best performing number of tasklets may be lower than 11 in these cases. The paper also shows results of strong scaling on 1 rank, on 32 ranks, and weak scaling experiments. You can find a lot of insights and key observations for all these experiments in the paper. Now let's take a quick look at the comparisons to CPU and GPU. These are the results for the performance comparison. We have some workloads that we identify like more pin suitable, some other benchmarks are less pin suitable, and these are the geomean values. So one key observation is that both UPMM-based pin systems outperform the CPU for all benchmarks except 3 of them. Another observation is that the larger UPMM-based pin system outperforms the GPU for 10 prim benchmarks with an average of 2.54 times. These 10 workloads have 3 key characteristics. They use streaming memory accesses, they have no or little inter-DPU synchronization, and they have no or little use of integer multiplication, integer division, and floating point operations. These 3 characteristics make a workload potentially suitable to the UPMM PIM architecture. We also have in the paper energy comparison, and we show that for 12 benchmarks, the 600 DPU system provides energy savings of 5.23 times over the CPU. Let's finish with some key takeaways. So one observation in our paper is that the throughput saturation point is very low for all operations and data types. So key takeaway 1 is that the UPMM PIM's architecture is fundamentally compute bound, and as a result, most suitable workloads are memory bound in conventional processors. Another key takeaway is that the most well-suited workloads for the UPMM PIM architecture use no arithmetic operations or use only simple operations like bitwise or integer addition subtraction. Another key takeaway is that most well-suited workloads for the UPMM PIM architecture require little or no communication across DPUs, what we call the inter-DPU communication. And key takeaway number 4 says that the UPMM-based PIM systems outperform state-of-the-art CPUs in terms of energy and performance on most PRIM benchmarks, and they outperform GPUs for a majority of PRIM benchmarks that have the 3 characteristics that we presented before, and the outlook is even more positive for future PIM systems. The UPMN-based pin systems are more energy efficient than state-of-the-art CPUs and GPUs on workloads that they provide performance improvements over CPU and GPU. And the reason is that both the source of performance improvements and energy savings is the less data movement between memory and processors that processing in memory systems can provide. So we know that data movement is a huge bottleneck in current computing systems. Processing in memory is a way of alleviating it, and UPMN is the first company that has fabricated and commercializes a real-world processing in memory architecture. Our work introduces this processing in memory architecture and programming model, characterizes it, and performs a benchmarking and workload suitability study. Our main contributions are a comprehensive characterization and analysis of this architecture, a new benchmark suite, the first benchmark suite for a real-world processing in memory architecture with 16 workloads. We have analyzed our workloads with strong and weak scaling analysis and compared to CPU and GPU. Key takeaways of our work are the workload characteristics for pin suitability, programming recommendations, suggestions, and hints for hardware and architecture designers of future pin systems, and the Print benchmark suite, which can be used as programming samples and also for evaluation and comparison of current and future pin systems. You can find all the details in our papers and all our codes, microbenchmarks, benchmarks, and script are publicly available in our repository. Thank you very much for your attention.